Hello and welcome to Ensemble Learning, Boosting Explained for Beginners. I am Kashif Murtaza, instructor at AI Sciences, and in this video I'm going to talk about boosting, which is one of the most famous techniques in Ensemble Learning. In this particular video we are going to talk a little bit about what in general Ensemble means or Ensemble Learning is, and then we will see how this particular technique boosting fits into the umbrella of Ensemble Learning, and we will also see one very famous algorithm that uses boosting. So let's dive in and see what is Ensemble. Ensemble Learning basically refers to the fact that if you, for example, have a training data and you have a lot of models to choose from, one way is to use all of the models, let's say KNN, let's say SVM, and let's say logistic regression, and maybe other models as well. Use all of them and use your training data, sometimes a part of the training data for each different model, and sometimes the whole data for every model. But one way or the other, give the training data or part of the training data to every model, every different model, and then the predictions from all these models, somehow combine these predictions in a particular way to come up with a second level or a meta model, and that kind of technique is known as Ensemble Learning. Now there are various techniques in Ensemble Learning that vary in the different settings how the ensemble is achieved. One technique is to select subsets or sub-multisets rather than feeding the whole data to each model. Other techniques, they actually vary in the choice of whether we are doing heterogeneous choice of different models or homogeneous choice of different models. And yet other techniques, they actually vary how we are going to actually combine these different kind of models together. What's the way of combining the predictions from different models? Boosting in particular differs from the other techniques in Ensemble Learning in a way that it actually trains the model in a sequential way that we will see in our next slide. It is not, all the data is not given to all the classifiers just in a parallel fashion. It is true that all the data is given to all the classifiers, but the classifiers are built in a sequential way rather than a parallel way. Let's see how it works. So in boosting, what happens basically is you have your original data, particularly all of the data, and you have chosen one of the models, let's say a classification model. And what you do is you just apply this, you just train your classifier on this data and come up with predictions. Some of these predictions on validation set is true, and some of these predictions, on training data, some of the predictions on training data is great, and several predictions maybe, or a few predictions are wrong. And here we are assuming this classifier is not really a very complicated or very flexible kind of classifier. Even a classifier that is better than a coin toss classifier in case of binary classification, just as good, and sometimes known as a weak learner. So what a weak learner is, it's a learner that has performance just better than half, or error rate is better than half. Maybe the error rate is 0.499999. Theoretically, it is still a weak learner, and that gives a very powerful kind of way of choosing these kind of learners, to not focusing on how complicated they should be. Any kind of learner that specifies or that is qualified to be called as a weak learner, that is just better by even a small margin than a coin toss based or a random classifier, is therefore as a weak learner. And it turns out only using weak learners, the learners that are very the learners that have very poor performance on the training data, when we combine them in a particular sequence, it turns out to be that the combination of these weak learners, the strong classifier or the ensemble classifier, is actually really, really powerful and much more flexible and great. So how it does basically is you have original data, you give to one of the models, if it's a weak learner, which means its performance or error rate is better than a half. It will perform well on some of the examples, and it will perform not very well on some of the examples. For the next classifier, the examples that are misclassified for the previous learner, a learner that is one step back to it, those examples are somewhat more highlighted than the examples that are classified very well. So, which means the next classifier or the model is forced to focus on the examples, training examples that are misclassified by the previous learner. And then that classifier actually make its predictions on all the data set, but its training has been done on the data set or the training examples that were misclassified so far. Now, this particular classifier or the model will produce some good results, and on certain examples, it will make errors. Now, the next classifier will actually be trained on the whole data, but the examples that are misclassified by the previous learner are weighted more or focused more. So what happens basically is the first classifier sees some data, classifies the data, and let's say there is some data that is classified well and there is another data that is not classified very well. The second learner actually focuses more on this misclassified data and focuses less on the data that was classified earlier very well. Now, this model will again have some results that are good, that are classified very well, and certain results that are not classified very well. Now, the next model will actually focus more on the examples that are not classified very well by the previous learner, and will focus less on the examples that are classified very well. And in a sequence, the classifiers or the number of classifiers will be kept on adding till the time that the required performance is achieved. So there are a lot of differences between boosting and bagging, for example. In bagging, all the classifiers, they are seeing certain subsets or basically sub-multisets rather than the whole data. All the examples for every model has the same importance, and all the classifiers, they are in parallel. There is no dependency of one classifier over the other, or there is no sequential learning. And then when the classifiers are combined together in bagging, they are combined in a way that all classifiers are of equal weight. In boosting, first of all, each model is seeing the whole data, and all the models, they are not in parallel. The examples that are misclassified by the previous model are focused more, so you are seeing all the data, but different examples, they are of different importance. And further, when all these different classifiers, they are combined at the end, different classifiers, they have different weights, they have different importance based on the error rate. The classifier with lower error rate has high weightage in the combination. So that's what boosting actually does. And in practice, boosting actually works really, really well and is very robust to overfitting. Let's see one of the very famous examples that fall under the umbrella of boosting, called era boost, or sometimes known as adaptive boosting. What happens is here, let's say this is your training data. And let's say this training data has, let's say 4 different samples. Let's say this sample, and let's say this sample, and let's say this green sample, and let's say this this sample, let's say. So, and you build a classifier. So let's say classifier 1 or model 1 that actually classifies well the, so let me name them rather than coloring them. 1, 2, 3, and 4. So it classifies well 1 and 3. So that's correct classification. And it misclassifies example 2 and 4. So that's what happens. So this information that it misclassifies example 2 and 4 is fed back to the training data, and example 1 got lower weight, which means it just got disappears kind of stuff. Example 2 got a higher weight. Example 3 got a lower weight, and example 4 got a higher weight. And then another model, let's say M2 is trained, and maybe this M2 classifies very well, let's say 2 and 1 maybe, and it misclassifies, let's say 3 and 4. So this information goes back to the next layer, and what happens is the weight of 1 goes even smaller. It goes to like negligible. The weight of 2 is got a little smaller than this one, but still bigger because yeah, the weight decay is sequential. 3, because 3 is misclassified and previously its weights were small, 3 will become a little bigger, but this 4, this will become even bigger. So that's 4. And now the next model, M3, will produce its results and so on. So how can we model this importance? So for example, here pictorially I'm saying that this becomes bigger and this becomes smaller and something like that. What happens basically is those examples that are misclassified in the previous classifier, they actually are associated with a weight. So for example, let's say x4 is initially x4 has weight 1/4, which means it is as important as the other ones, 1/4, and x3 is 1/4. But after this, the weight of 1 and 3, they go down. Maybe, for example, 1/8, or maybe the weight of 3 is, let's say 1/8. And the weight of 2 and 4, that goes up. So the weight of 4 may go up to, for example, a 1/4, or 1/, for example, 3, and the other weight, such that all the sum of all the weights that turns out to be 1. And when this when the error rate is being computed, what happens basically is if the model misclassified example 3, then the error at example 3 is basically example x y3 prediction. If that is not equal to true y3, if that's an indicator variable, which means 1 or 0, then it is multiplied by the weight of these 3. So if the weight is higher for a particular example, the importance of error becomes higher, and the algorithm is forced to reduce the error, and the error is now weighted. If you misclassify different things, the error caused by each misclassification is weighted by the importance of these samples, and this importance is coded with respect to these kind of weightings. And now progressively the weights of different samples, they got increased, the weight of different samples, they got decreased, and eventually the classifiers, they kept on adding as the required performance, till the required performance is achieved. Further, these different classifiers, M1, M2, M3, and so on, they have different error rate, which means depending upon the importance of the samples, what is the error rate of M1, what is the error rate of M2, what is the error rate of M3 in sequence. And depending upon the error rate, for example, if the error rate of M1 is 0.4 and error rate of M2, for example, is 0.2, then the weight of this classifier in the combination is smaller than the weight of M2. So the classifiers or the models that have lower error rate are weighted more in the combination. And these two properties, so the highlighting of making the prominent misclassified examples more and more through weighting, and then actually combining different classifiers based on deciding their weights depending upon the error rate they got, that actually is overall called adaptive boosting or AdaBoost, and it's really, really powerful method ensemble method. One note that in the original implementation of AdaBoost, these weights are computed iteratively. As these models are built in succession, the weights are computed automatically. So the combining step is not carried out independently after all these kind of trainings. After each iteration, the weights are adjusted, and at the end, just they are combined based on these weighted average. So let's go to Python and see how AdaBoost works in Python. So here. So that's the iris dataset with 4 features and 3 target labels. I'm splitting the data into training and test set, 30% test and 70% training. So now I am loading from scikit-learn.ensemble. I'm loading the AdaBoost classifier. That's how I call the model, and .fit function will train on the training data, and .predict function will actually predict on the unseen data or the testing data. And here I have loaded the matrices, and I have picked the accuracy score to just see the accuracy for this particular classifier. And it turns out that the accuracy for AdaBoost on this simple kind of data set is 93%, which is great. So basically that's about boosting. We have videos on other ensemble methods like bagging and stacking as well on our channel AI Sciences. We also have all these kind of explanations of single model training and the details of each model. If you see the link in the description of this video, you will find out all the routes to reach to further videos and courses that explain each of the bit in length. So if you like this video, please press the like button, subscribe our channel, and share this video with your friends. So hope to see you next time.